How about everybody copy this down and leave Addison alone? Daniel. Look, don't make me bring out the jar. Thomas and Selena know about the jar.
I've heard the jar.
I will make you right. I will make you right. Asked Addison if he was in charge of catheters on the back of your bathroom pass and turn it in to me. And we'll put it in the jar, Daniel, if you can't be nice.
I remember Alex took one of them that made fun of Brent's lack of
Yeah.
Shortly after one was turned into about.
Record that conversation. I paused it on purpose. Our first limit here, our limit of f of x is infinite. Our limit of g of x is just L, so just some number here. So our sum and difference properties apply here. So if I'm doing the limit as x approaches c of f of x plus g of x, f of x is infinity, g of x is L, but what is infinity plus another number? It is still infinity. So when Buzz Lightyear says infinity and beyond, it's really still just infinity. These are just like facts that they tell us from the beginning. Yeah, so those are just like facts. So for this particular set. So, alright. Okay, for number 2, if I've got f of x times g of x, f of x is infinity, and I'm multiplying it by L, it is going to give me infinity as long as L is greater than 0. So as long as this is a positive L right here, I'll get positive infinity. But if I do infinity times a negative number, you get negative infinity. Yes. Yes, if you were multiplying, if you just multiply by like a negative 1, instead of going to positive infinity, now it's negative infinity.
Wait, so that's a negative sign?
Yes.
No, these are multiplication. Because this one's for L is less than 0. So that's a negative L there. It's negative value. And for the quotient, if we have g of x, which is L, divided by infinity, it is going to give us 0. Okay, so it doesn't matter what number you have. It doesn't matter whether it's 1 or 7 or negative 3 or 1,000 or 1,000,000 or a gazillion. If you divide it by infinity, it's going to go towards 0, right? Because infinity is infinitely bigger. Think about having a fraction of like 1 over 1,000,000. It might as well be 0, right? Well, if you could have 1 over infinity, if you could actually get to infinity, it would be 0.
Negative infinity would be? I don't understand. Oh. I understand. It's a concept.
You have to think of it like a limit, which we're going to do later, so I'm not even going to go there, okay? I'm not going to go there right now, because we're going to do it later today.
By infinity, just that, it's approaching.
And so this also applies whenever you have negative infinity as well, so I just didn't list the separate properties for that. So, whenever we're doing something like number 6, we did something similar to this in the warm-up, right? So if I plug in 0, I'm going to get 1 over 0. I get undefined. That tells me the limit does not exist. But if I want to know if it's positive or negative infinity, I can do the limit as x approaches 0 of 1 plus the limit as x approaches 0 of 1 over x squared. So I can take the limit of these two pieces, the 1. No, it's the one that's right here.
Oh, I see. I said tripped me out that there was a limit on the left.
You take them apart if they're multiplied or just...
Yes. For limits, you can also take them apart if they're multiplied. So like here, the limit here is just 1. This limit, I need to do a table for, but it's a much easier table than if I am doing the table for 1 plus 1 over 1 squared. So if I do a table here, we're approaching 0. If I go from the left, like if I did negative 1, I'd get 1. If I did negative 1/2, 1 over negative 1/2 squared would be 1 over 1/4. So I'd get 4. What would you get for negative 1/10? 100, because you got to square it. So that's going to positive infinity. You should also probably technically check from the right as well there, I guess. I guess we should. To confirm. So you would have 1 here if you do a positive 1/2. Does the sign make any difference here? Because you're squaring it, so you'd get 4 here. If you did 1/10, you'd get 100. So we're going to infinity from both sides, so this is infinity. What is 1 plus infinity? Infinity. No. If it was negative 1 times infinity, it would be negative infinity. Because when we're multiplying, negative times positive gives you a negative. But if it was negative 1 plus infinity, it's still infinity. So like if you subtract 1 from infinity, it's still infinity.
How do you not understand that? Tommy, it's because it goes on forever. So it doesn't matter if you add or subtract anything from it because it goes on forever. Now if you multiply it, that's different.
Since infinity's not actually a number, like we have a gazillion and we subtract 1, then we have 1 less than a gazillion, right? But because infinity's not actually a number, because it's more of an idea than a number, since it's the largest possible, goes on forever, never ending, even taking away 1, you can't say that's 1 less than infinity because infinity's not real. It's not actually a number. Just know that if you take anything and add infinity to it, you're going to get infinity. So infinity's just going on forever, right? It's like if I want to do infinity, if I want to write down infinity, I would just do this all day for the rest of my life. And if I never died, and if I never ever died, and I never ever ever quit putting zeros, and my life went on forever, eventually that would be infinity. So if you took away 1 from that, it doesn't matter because I'm still here adding more numbers, right? Right. Right.
All that matters is when you get infinity and minus 1 plus 1.
Okay, let's go to number 7. He's got it. Come on, let's go. Next problem. All right. All right, so if we plug in -2, we're going to get a 0 in this denominator right here. But we do have a 5 in the numerator here, so it's like 5 over 1 over 0. But you're getting that undefined here. So what we want to do is, with limits, we can take the limit of a numerator and denominator separately. So in the numerator, we can do the limit as x approaches -2 from the left of x squared minus or plus 1. Over, and then we can do the limit separately in the bottom. So in the top, we could just plug the number in, -2 squared plus 1. It's going to give us 4 plus 1, which is 5.
So for that, is it possible to flip the second multiplier? Yeah, that's what that
I don't think you can flip the second and multiply whenever you have a 0 in the denominator.
Whenever you have a 0 there? Okay.
Denominator. I don't think. All right, and so then we would only just have to make a table for this bottom part. So we're approaching -2 from the left. So like -3 would be 1 over -3 plus 2. Should give me 1 over -1, so I get -1. If I did -2.5, which I'd really rather do a fraction, so that'd be 5/2. All right. 1 over -2. Make sure I'm right. That'd be -2.5, which is closer to, yeah.
So then you do like 21.
So I get -1/2 here, which will give me -2. And then negative. No, you're right. 21 over 10. Because that would be 2.1, -2.1, right?
Yeah.
So 1 over -21 over 10 plus 2 would be 1 over -1/10, right? And -10. So what does it look like is happening here? Negative infinity. What is 5 divided by negative infinity? Zero. If infinity's in the bottom, it's so much bigger than anything else that could possibly be on the top that it's 0.
The properties I don't understand. It's like 0.0. It's super small.
Right. It's so tiny that it's 0. Yeah.
If you were dividing something from infinity, infinity was on the top of it.
Yes. Yeah. Like if you had to do infinity divided by 5, it would be infinity. Because infinity's so big that even if you divide it, it's still infinity because you're still putting zeros on the end. Or 9s or any numbers.
That would be 0.
Excellent question. No.
What? How? Because you can't do it. That's the same thing.
This is another version of the indeterminate.
It's obviously one.
It is. It has to be one. I'm calling the Harvard mathematicians out. That's his point.
It's like having 0 over 0. You cannot determine anything
That's
from it.
1 to the power.
But it is infinity itself.
Oh, well, it could be different.
We're doing 5
it-
divided by 5.
Infinity over infinity is another version of indeterminate. And we were leaving it at that. Okay. Alright. We're going to leave this section. We're going to go to the next. Alright, we got to shift gears a little bit here.
Wait, this high. If I want some water, would I have to
Yes.
Dang, it's like it's gonna dehydrate.
If you surely you won't dehydrate during calculus.
She's gonna move over and I'm gonna be on the ground passed out.
Look how good that was. God, look how hydrated that was.
All right, everybody. This should not say 3.5. I changed it. It should say 1.15. It used to be 3.5. It's 3.5 in your book.
Is this a new paper?
Okay.
Yes, yes.
Okay. All right. All right. I'm gonna have to get the jar back out.
Whoa.
Freshman year vibes.
It's like nothing ever changed.
Literally.
Then whenever Thomas refuses to give up his bathroom pass for punishment, then I might have to send him to the office.
No, I mean exactly like that silence. I won't be able to sing it.
So you're saying the jar would work, and I should get it out.
Yeah. I mean, he's not wrong.
If I don't do that, then what is possible? You should find out.
Is that an R above the X?
Yes.
Oh, I can do it. Oh, you should do
Have a reunion for just that one class.
We should bring everyone back
Yeah.
That would be
for one class.
No, I'm working that bad.
Oh, we're missing Luis today.
He was on the field trip. Oh. He got sick.
Okay. All right, we're missing Luis. I need to change that from attendance.
What kind of feeling will? Yeah, what kind of
Because I was just trying to think, and Luis was in that class also, wasn't he?
Yeah.
Me and him did something at the board office this morning, out right there. We were right beside each other, but we had a nice.
Hopefully he's not bad sick.
That's what you do. Wait. Slow down.
I meant to hit the freeze button.
See, look, maybe that right
Come on. There we go. All right. It's an R. A 2. Okay. So, we have basically already talked about this idea. Today, we will be looking at limits at infinity. Very similar to the title of 1.14, which was infinite limits. So, our difference in these two sections is yesterday at the beginning of this class, we were looking at limits where the answer was infinity. Vertical asymptotes where we either approach positive infinity or negative infinity. Today, we are going to be looking at x approaching infinity. Okay, so today our infinity is going to be down here. The answer still could be infinity, right? It still could also be an infinite limit, but it won't always be. If r is a positive rational number, rational means we can write it as a fraction, and c is any real number. So c can be positive or negative, but any real number. So basically we have a number divided by x to some power here. It must be a positive power, Because what happens if I have 1 over x to the negative 2? We got a switcheroo here, and that's got to come to the top, so we really don't have an x in the denominator if my exponent is negative there. So, am I recording? Okay. All right. So any number divided by x to any power is going to be 0 as x approaches infinity. So think about the very simple case of 1 over x. So if you think of like a table for that, don't think of 0 because you got to first glass and tape there. But if I think of plugging in 1, that's 1 over 1. If I plug in 2, that's 1/2. If I plug in 3, that's 1/3. If I plug in 10, that's 1/10. If I plug in 100, that's 1 over 100, right? So those fractions are getting smaller and smaller and smaller and smaller and smaller till eventually they approach 0. Okay? It doesn't matter if I square that right there, then it's just squaring that denominator, which is going to be 1/4, 1/9, 1/10, 100. So it also goes to 0, and it goes there even faster, right, if it's to the second power. Third, fourth, fifth power, 1/2 power, as long as it's a positive power, it's going to approach 0. So if we look at example 1, we're supposed to do the limit as x approaches infinity of 6 minus 3 over x squared. So it is not going to be 0, but you corrected yourself as you were saying that. We're taking the limit of 6 and 3 over x squared separately. So the limit as x approaches infinity of 6, what's that going to be? 6. There's no x to plug in. It's not 6 over.
Where do you see that?
There's no x to plug in, so you're not plugging in infinity anywhere. You could, if you wanted to be wrong, you could. So just any limit whenever it's a constant number, like if I do the limit as x approaches 2 of 7, what's that answer? 7. Correct. For the second part, it's 0. So the second part, the limit as x approaches infinity of 3 over x squared, this is going to be 0. Right? Because if you think of what's happening there, you don't have to make a table, but if you did, if you plug in 1, you get 3. If you plug in 2, you're going to get 3 over 4. If you plug in 3, you get 3 over 9. Plug in 4, you get 3 over 16, right? So that's getting smaller and smaller and smaller and smaller. It doesn't matter that the top is 3. It goes a little slower, but it eventually still goes to 0. So if you got an x in the denominator, it's like you're plugging infinity in there. You're going to get 0 here. What is 6 minus 0? 6. I said you were incorrect at first, but then you corrected yourself. Yes. In a way, it's like you're plugging infinity in there. Yes.
So why do sometimes we plug in like we plug in if x equals to 0, we plug in 0, and then sometimes we plug in like the values we come to it, and then
So if you can plug in the number, that's what you want to do. So like if we're looking at the values leading up to it, then we have already plugged in that number, and it gave us a number over 0. So
it's like, but it still gives you the same thing as it approaches something different. Like it gives you a y value.
yes, yes. So if you can plug that number in, it's going to give you a correct y value.
But even if you can plug in the number like 0, that doesn't mean that there's not a hole. There can still be
Right, there could still be a hole. That's correct. Yeah. Okay. All right, here's our next one. Okay, I see a lot of cell phones out. I feel like they're not necessary or helpful at this point. Alright, so for this one, we're doing x approaches infinity. But, like, if I was thinking about it like I did the last one, if I tried to plug in infinity, I get, in the top, what's 2 times infinity? Infinity, and subtract 1 from it. It's still infinity. What's infinity plus 1? And what did I just tell you guys infinity over infinity is? Indeterminate. Yes, very much so. So, indeterminate means keep going. You got to. So, it doesn't necessarily mean there is an answer or there's not an answer, but it means that you can do something else.
Are we going to?
We are, yeah. So, here is what we're going to do. All right, I'm going to divide every term by the highest degree variable from the denominator. What is our highest degree variable from the denominator in this particular case? It's the x. So you're looking at degree means the exponent on the variable. So, I mean, in this case, you just have the x. But if I had an x squared down there, I'd divide everything by x squared. Whatever the highest exponent is there. So what I'm doing is I'm dividing every term by x. And this is okay to do as long as I divide every single term by x. I'm going to write this probably a little longer than you would have. Because I said to do it this way. We'll see what happens here whenever I do this.
If x approaches 0, then it would be 1.
Okay, so right here, these x's can cancel. And these x's can cancel. So right here I'll have a 2 minus 1 over x in the numerator. What do I get when my x's cancel here?
1.
That's a 1. Make sure you don't just make them go away, because x divided by x is 1 plus 1 over x. You are going to use the highest degree variable from the denominator. So in this case, variable, that was the x. Don't use the coefficient with it. There wasn't one here. We'll do a few more so you'll see. But we just divide everything by that highest degree variable. All right, so this is good. What we did here is we turned it into a complex fraction. Usually we don't want complex fractions. Usually we want to get rid of those, right? And if we wanted to simplify this, we could multiply by x and make it back into what it was. But we want a complex fraction here because our properties of limits tell us that we can take the limits of all these pieces separately, right? So we can take the limit as x approaches infinity of 2. What will we get? 2. What about the limit as x approaches infinity of negative 1 over x? 0. So because if I've got 1 over x, as x gets bigger and bigger and bigger and bigger, we got 1 over 10, 1 over 100, 1 over 1,000, 1 over a million, we get closer and closer and closer to 0. So if you have a variable in the denominator, a number over a variable, then it's going to go to 0. So, right. So like, whenever you're plugging in small numbers, it's going to be a big difference. But when you go to infinity, it's going to be like that 1 over x isn't even there. Right? So it goes to 0. What's the limit as x approaches infinity of 1? 1. What's the limit as x approaches infinity of 1 over x? 0. So we got 2 over 1, which is just 2 here. So that limit is going to approach 2. It is also important to note this is your horizontal asymptote of your graph because it's still going to be 0.
Wait, no, like, if it's x squared for, like, let's say the beginning.
I think maybe the next one might do that. So let's look at that. Yeah, the next one does that. So let's look at this one.
Thank you for that.
Alright, so we're going to do the same thing we did for the last one. So you want the highest degree variable from your denominator.
X squared.
So it's the x squared. You do not have to use the coefficient with it. Just divide everything by x squared. Has to be from the denominator. Alright, so I'm going to go ahead and reduce here if that's alright with you. 3x over x squared, what's that going to give me? 3 over x. And then I've got minus 1 over x squared over, here my x squareds cancel, so I just have a 2 plus 5 over x squared. So anything with an x in the denominator is going to approach 0 as your numbers get bigger and bigger and bigger. Yes?
What happens if x squared on the numerator?
One of the, since we had an x right here, it canceled with one of the x's here. And so the limit as x approaches infinity of 3 over x, that's 0 because you got a variable in the denominator. What about 1 over x squared? 0 because you got a variable in the denominator. What about this 2 right here? 2. And then what about the 5 over x squared? 0. So anything with an x in the denominator, as x gets bigger and bigger and bigger and bigger, it's going to go to 0. So this gives us 0 over 2, which equals 0. Okay, here's a couple more. I'll let you try them. Yes, 2x to the second. It's kind of an ugly 2 there. What do I divide by on example 5?
X cubed.
The highest
X squared.
from the denominator, so it needs to be x squared.
Oh, 5? I thought you said
Yeah.
4. Yeah, I did that right.
Yep. So you get 3/5 for the example 4.
Yeah, 3/5.
We're okay there?
I'm doing number 5 right now. You just gotta remember your properties.
Alright, so for example 5, when I cancel right here, I get x to the third over x squared, so 2 of these are going to cancel, but I've got an x, and it's in the numerator this time, right? It wouldn't really help you get anywhere on this, because you don't really want it to be multiplied together. You could, but it wouldn't help so much. So I would still do what I've done here. So let's just tell me about this 5 over x squared. What's it going to go to?
0.
That goes to 0, right? What about the 1 over x squared?
0.
That goes to 0. So with the infinity, it's like we're plugging in infinity, right? So let's think of this like we're plugging in infinity. So I've got 2 times infinity plus 0 right there. And then 3 plus 0 on the bottom. So when I do 2 times infinity plus 0, what would I get? Infinity. On the bottom, I'll have 3. What is infinity divided by 3?
Infinity.
Infinity. So infinity is my answer here.
I like infinity. You don't even have to think about it.
Yeah.
It just is.
Yeah, it just is.
No fractions over to the side or long division or anything.
Yeah, I think.
We've never really implemented infinity until
No. All right. Questions?
Aside from graphs, like, we never, like, equations.
All right. Here's our next one.
Well, you have to do the coefficient thing, not coefficient, the other thing.
The
No, you can't do that, never mind.
rationalize it? No, you can't.
Like double square it, like so we can get rid of the.
But then you have to square the
It's
top.
DNA.
You can't square top and square bottom fraction
It's DNA.
because it's not equal to itself. Like if you take 1/2 and square top and bottom, it's 1/4. It's not equal. Thomas is just going to
When
leave
you
it off.
split it first, and
Do
then
it like the last problem.
I say,
Which once again is okay if he wants to be wrong.
Got 'em. That's brutal.
would you split them first and then?
Okay, so the numerator is not underneath the square root. The denominator is underneath the square root. So I'm going to divide by x squared here. But this whole thing right here is under the square root. So I am actually dividing by the square root of x squared. What is the square root of x squared? It's x. So in the bottom I'm dividing by x squared, but since it's under the square root and the top is not, I'm just going to divide by x.
Oh,
What?
what?
Because the square root of x,
That is how a square root
No.
square root of x squared is x.
Somebody get Thomas the jar. He's making fun of me. He's causing me to can't handle his own thing.
Alright, I think I might need to break y'all up over there. Alright, 3 minus 2 over x over, we still have the square root. We got 2 minus 1 over x squared. Okay, so limit as x approaches infinity of 3 is 3. 2 over x,
0.
that goes to 0, so 3 minus 0 is on the top. I've got this square root here, but our properties of limits let us take the limits of what's inside of that square root and just leave the square root there. So I'm going to have 2 minus 0 here. So I've got 3 over root 2, and you can leave it like that. If you're doing one like this in your textbook, they probably do rationalize and call it 3 root 2 over 2. But it's fine to leave it as 3 over root 2.
Have you had a kid crying calculus about like?
Yeah, there's usually at least one
How could she not?
a year crying in calculus.
Yeah.
Yeah. I mean, there's probably way more than one outside of class, but in class, there's usually at least one.
Not in class.
Yeah.
I probably will. Towards the end of the year, I'll have a breakdown.
Yeah, I'm gonna see.
I can't remember her. Yeah, I can't remember that, but if she cried in class, but yeah. There's been more than one at home, I'm sure, but
This is the easy stuff right now.
I think she usually was pretty composed in class.
Give me the homework.
Alright, okay. Hold up. You can't do the homework yet. Alright.
We're doing a lot of
I like you.
Now you might look at this and say, hey, that's the exact same problem we just did. Alright, pay close attention to this. It might blow your mind. Okay, so this may blow your mind. Pay close attention. Alright, so just like the last problem, because this is essentially the last problem, except for this time it's negative infinity.
Yeah.
Alright, in this denominator, what I need to do underneath that square root is divide by x squared. Okay, here's the problem. This time we are approaching negative infinity. So that means the numbers we're plugging in are like negative 1 squared, negative 5 squared, negative 100 squared, negative 1,000 squared.
But wait.
What is it?
So what do we get whenever we
You get 1. Like 1, the square root of 1.
get a negative 1, a negative 5, a negative 100, a negative 1,000? Alright, so if, you want to write this down, if x approaches negative infinity, the square root of x squared equals negative x.
Okay, hold up. How is negative 5 squared? The square root of that,
Okay,
negative 5.
I'm gonna give it to you. Okay, you square it inside there.
Okay.
You square it again.
No, okay, what's negative 5
Negative
squared?
5 squared is 25.
Then what's the square root of 25?
Oh my God! You're squaring it, and then you're taking the square root of it. Yeah, do that. Do that for 5. They simply cancel. Do it for 5.
But if you, I understand what you're asking here, like if you square it first, it's positive, and then you take the square root, so you would get a positive there. But we also have inverse operations happening here. So when we're dealing with these negative numbers, these inverse operations are canceling each other out. There could be a way you could
I see what. Oh.
notate that But this is just this is a fact you have to know for these limit problems. Okay? So, if you are approaching negative infinity, you're going to divide this by x squared like you have been doing. But up here, you've got to divide by negative x.
Not negative x squared, just negative x.
Just negative x. So the square and the square root still undo each other, but because these are negative values, we want a negative x there. So we get negative 3 plus 2 over x over the square root.
Oh wait, because no, it's negative x. You're right. I'm trying to keep it. I'm doing proud of you. I'm going to keep question. Proud of you.
So it's just like the last problem we did.
Yeah.
But in the last problem that we did, all of our x values were positive. X squared, sorry. So x squared, x squared equaled just regular x because everything was positive numbers as we approach positive infinity.
Oh, so you just divided it.
So up here we're dividing by negative x this time instead of positive x.
Gotcha.
So what that's going to do, we're going to have a negative 3 plus 0 over the square root of 2 minus 0, so we get negative 3
Which is the same
over root 2. Same as the last problem, except negative.
So the x approaching negative infinity only affects.
Pretty much. I mean, it is possible to approach positive infinity, but have a negative answer, so it'd be opposite sign of whatever you get if you just do it regular. Yeah, it's pretty much just going to be opposite sign.
So x approaching negative infinity only affects the numerator. Is the denominator is like still x squared?
Yeah, this stuff's still under the x squared, so you got the square there, so you don't change signs there. It's just the part that's not underneath the square root, which in these has been the numerator. It is possible for it to be switched where the square root's on top. But
So I was right. It's the exact same answer to the previous problem.
yeah. Correct. It does not matter if it's positive or negative infinity. Anything with an x in the bottom still equals 0, even if it's negative. There. So you can ignore it for most of these problems. It's just the square root where you need to know where it's negative infinity. So like if I go back to these I was doing here that we were feeling pretty good about, if I change this where it was x approaches negative infinity, I would not do anything differently. Because even if it's x approaches negative infinity, it would still equal 3/5. Okay? It is only when you have the square root that you're going to have that problem. Yes. Correct. All right. Try this one. See if you got it. Put your phone away. Please don't make me have to ban them and take them away from you.
It was actually a necessity.
All right, try this one. It's a necessity.
There's another one? No. They just don't talk.
Isaac Newton.
Yeah,
Actually, there were other mathematicians that came up with limits before him.
He's the one that.
But he's the one that put it all together. Yeah, he put it all together. Not yet. We will eventually. The understanding of this is what we need to be able to do derivatives. Derivatives are useful for lots of different scenarios, but we're still ways away from that. So, just the beginning. We're doing pretty good. We're as long as we don't get behind where I'm going to be at home a few days, we should be like one day ahead of schedule. So we're doing okay. Yeah. Considering that I taught zero limits in pre-calculus and I normally teach limits in pre-calculus, I feel like that's pretty good.
That's why it feels like I'm learning.
Yeah. Yeah. Okay. So for this one, you're going to divide by x squared. This is under the square root. Which, since this is x approaches negative infinity, what do I divide by in the top?
Negative x.
Negative x. So I get the limit as x approaches negative infinity of negative 5 minus 1 over x over the square root of 1 minus 3 over x. And then all this stuff with x's in the bottom is going to be 0. So I got negative 5 minus 0 over square root of 1 minus 0. So it's just going to end up being negative 5.
That's what I got. Let's go.
Yes.
Why don't you have like why isn't it 5 over the root? Yeah, that's what I was.
It is 5 over the root of 1, but what is the square root of 1? Is 1.
But on the one before it.
So before, the square root of 1 is 1. So you're doing negative 5 over 1. I don't think it should have went away. Okay. Yeah, it's there. Okay, I gotta show you one more thing. Copy these two down real quick. I promise, this is easier than the square root stuff. This is easier than the square root stuff, I promise. I promise these are easier than the square root problems. Oh my, Noah, that attitude. I don't know why you decided to sign up for calculus. Huh? That is if x approaches 0. But x does not approach 0 here. It's infinity. Okay, tell me about sine. Sine of x. What's the biggest it can be? 1. What's the smallest it can be? It can be negative 1. Negative 1. So when I have, so unit circle, the biggest it ever is 1, like at the top of the unit circle here. That's y coordinate. It's 1 right here. And the lowest it ever goes down here is at negative 1. Alright, so sine is always between 1 and negative 1. Same thing for cosine. Cosine is also, negative 1 is always less than or equal to cosine of x less than or equal to 1. It's always between negative 1 and 1. So, this number right here is always something between negative 1 and 1. That's a really small number, right? So as x gets bigger and bigger and bigger and bigger and bigger, what is this going to approach? Okay? Sine of 3x is like just having a 1 or a 7 or a 52 up there. Okay? Treat trig like it's just a number because it is going to have like some tiny oscillation where it's going back and forth. But as you go on, that number on the bottom is so big. You know, you might have negative 1 over 20. You might have 1 over 50. You might have negative 1 over 1,000. It does go back and forth from positive to negative just a little bit, but it's such a tiny amount it doesn't matter. It's going to go to 0. Yes?
So, basically, we just plugged in infinity to the bottom, and that's how we got to it.
More or less, yeah. Yeah. Because it's like having a number over infinity.
So the same thing happens for example 7.
So it's all,
Infinity goes in the bottom, and it's 0.
part of this is 0.
Oh.
Because
There was
divide everything by x first, because you got a fraction here. You got 2 minus cosine x over 1. So just like we did on the other problems, I'm dividing everything by the highest exponent in the denominator. Uh-huh.
How does the x and cosine not cancel?
Because this is like cosine of x, you're taking cosine of it. So it's not cosine times x. Yeah, cosine is like a function. It's like you're taking natural log of something. Yeah, so it's like an f of x. So you can't just cancel those out. Right.
So then, now that you got cosine of x over x, that is 0.
That's 0 because cosine, you can think of it like just having a 1 over x there. Because cosine is a really small number, something between -1 and 1. So 2, 0 over 1, and you get 2. So if you see sine or cosine, treat it just like it's a number over x. Okay.
So when this says,
What we
so
got
can you
tomorrow is
even plug negative infinity into cosine x?
No, but treat it like it's a number. Treat it like it's just a 1 over x. So it's
treat
0.
like cosine x as its own variable.
Yeah, if you have sine or cosine, treat it like it is just like a number.
Oh, they're using x there.
Okay, yes.
I was going to picture this.
As long as it's over a variable, yes. Yeah, so like, so the limit as x approaches infinity of sine x over x to any power, it could be to the first, second, third, fourth, it's going to always equal 0. Same thing for cosine. 1 through 6, 13 through 35. Here, let me look real quick just to make sure I'm not giving you something too crazy that I've forgotten about. It's possible. Okay, 1 through 6 is just matching. Think about where you would have vertical asymptotes. Think about where you would have horizontal asymptotes for that. And 13 through 35. Bye.
Yeah, I'm currently dehydrated right now. I need water.
I think you'll make it. Tomorrow and Thursday, I'm gonna zoom in and teach you things from my house. So, Alfredo, can you be the subs helper with the computer if she needs it? I'm gonna email you guys all a link. It'll probably be better though if you watch on the projector, just because like all the sound's going bad. So if you could log into yours on your email on my computer and go to that link, then I'll be on there for that. And I'll leave my. Yes, I'll give you it. Well, we probably won't do a warm up tomorrow since I won't be here. So we'll probably just check homework and yeah.
check it over the Zoom.
I could, yeah.
Show
I
it up.
could. I might do that actually, yeah.
Walk
That way I
up
don't
to
have
the
to, yeah.
camera.
Have you line up. You too.
It'll be interesting virtual class.
Yeah, I was hoping I wouldn't have to do that ever again in my whole entire life, but I also am not surprised.